everyone, welcome to my talk. As Jens Eisert has just highlighted, there are exciting developments. But before I show you how Quandela is intending to bridge that gap between NISQ and the fault-tolerant regime, Quandela is new to Bitkom, so I want to give you an introduction into the company and tell you where we are right now before telling you how we get to the fault-tolerant regime. So Quandela at a glance, so we were incorporated in 2017. It's a French company. It's built on 35 years of scientific research at the CNRS. It delivered its first commercial quantum device, a single-photon source, in 2018. We have now 100 plus, actually 120 people, with more than half having PhDs in all sorts of fields, not just physics. We have 2 production facilities near Paris, in Massy. And we have 4 main locations worldwide, headquarters in France. We have a subsidiary in Canada, we have a subsidiary in South Korea, and we have the Quandela GmbH in Munich, which I'm going to talk a little bit more about later on. And we are about to open more subsidiaries as well. We have prominent scientists in the team, Pascal Senelard, who is well known and who is part of the French Academy of Sciences. There is Alain Aspect, a Nobel Prize winner. He's on the scientific board, and we have many patents and scientific articles and many citations in the team. As I said, Quandela is a full-stack quantum computing provider. We do hardware manufacturing. You would have seen some of that in the video. We build our own quantum processors. We have our own open-source programming framework. We work on quantum algorithms, and we also have a cloud presence. And I encourage you to check that out. So we are in the process of industrializing the production of photonic quantum computers. We have a quantum computing factory where we assemble our quantum processors. We have our own clean room where we fabricate our qubit devices. And these are the secret ingredients of our technology. That's how it started. This is a single quantum dot source, so it's etched out of a layered gallium arsenide wafer. At the center of this cross, deep in the material, there is a quantum dot buried, and if you excite with a laser pulse, you get a single photon out of very high purity. And that's the secret behind our technology. So what do you do? So this is a bit of a switch. Normally, when you think quantum computing, you think about qubits and gate-based modalities. Photonic quantum computing is different. So here is the simplest form of photonic quantum computing that you can do. You have your single photon source. You send the single photons come out one by one, typically at the moment at the 80 megahertz rate. They go through this box. This box sorts the photons and makes sure that these photons can are sorted to these different channels. There are delay lines in here, such that the photons, and here in this case 6 photons at a time, arrive at the core of the photonic quantum processor, which is this photonic chip, which has interferometers on it and corresponds to a unitary transformation between the input port and the output port. So the photons enter here. They probe this maze, get entangled, and then you detect the photons at the end. In single photon detectors, you count your photon arrival events, and that gives you the result of your calculation. And you have full control. These white dots, they're thermal phase shifters. They allow you to program any unitary matrix you like in that chip. And this modality is called boson sampling, typically. And it's in principle high speed, high precision. You can repeat this as many times as you like, and it's robust to noise. That's a big advantage of photons. They don't dephase, they only get lost. And when I say only get lost, this is of course our big enemy. Losses are the big enemy. That's what we work for every day, to reduce these losses. And I'll come back to this topic later on as well. Okay, so this is how it works. This is the architecture again. This was already put together in 2022. The paper, which you can find here, appeared last year. This is our 6-qubit platform, again with a quantum dot source, a so-called demultiplexer, sorting the photons, the interferometric chip, the detectors, and of course, the classical machine that controls the platform. This is how it looked in 2022. This is how it looked when it went to OVH Cloud in late 2023. So the processors are now in a rack server format and can be easily wheeled into an HPC center, plugged into the socket, and they run. Okay, so there is no setup required. They're HPC ready, these computers. So we have further deployed 4 systems over the past 20 months. and we directly integrate them into HPC environment. Notably, I just want to point out our Belonos machine, the 12 qubit machine is about to be delivered to within the Euro HPC initiative. Actually, the machine is called Lucy, I believe, but it's a 12 qubit machine which goes into Gensi next month, essentially. And we, of course, have our, in order to control the hardware, we also have our software stack, Percival, which allows us to control the machines. All right, but because photonic quantum computing is a little bit unusual, you also need to develop your ecosystem, and so we develop together with industrial clients, we look at use cases, potential use cases, applications, and we co-develop software solutions with them using the cloud and based on the expertise in our quantum algorithms teams. At the moment, we have 15 corporate clients, 5 of which are in the Global 500. You can read the names here. I'm not going to go into detail. We work across different sort of topic areas or machine learning, simulations, optimization, and also cryptography. Now, it's important to make one disclaimer here. We work with these clients because at some point, the hardware, the Quandela hardware, will provide an advantage. At this stage, all that we do, you can still simulate in principle on a classical machine. But at some point in the future, we expect to have a real quantum machine that brings the actual advantage. I just wanted to highlight that here. But the point is to work with your clients and your customers early so that you can develop use cases, so when the hardware is ready to provide the quantum advantage, we're there and the customer knows what to do. This is just a snapshot of the different use cases. So we have use cases in finance, in chemistry, in aerospace, energy, pharmaceutical, and cybersecurity. And you will notice that a lot of the use cases are actually sitting in the hybrid quantum AI space. So a lot of it is just classification. For example, interesting application in finance where you can classify portfolios and you can identify fallen angels early on, and you can show that there's an increased accuracy in principle with quantum solutions. Then you have battery optimization or polymer identification. On the other hand, we also do, not in the quantum AI space, infrastructure modeling, and we also work on cryptographic keys. One use case I just want to highlight is the use case in the context of the BMW Airbus challenge from last year. There was a global challenge in quantum AI space, and Quandela actually won this category. The task was to generate nighttime images from daytime images using a quantum solution or a combined classical quantum solution. Now, I'm not a AI expert by no means. I'm an experimental physicist, so I will stay away from trying to explain to an audience that is potentially much more an expert than myself what this is about. But just to highlight, there were two modalities. So there was a quantum GAN and a combination of classical and boson sampling. This means boson sampling, okay, just to be sure. With these two modalities, the team was able to show that there is actually an advantage, okay? Now, to cut a long story short, if you're interested in this and want to hear more about the intersection between, or the interface between quantum and AI, please, I encourage you to see Jean Zenela's talk, to attend the talk tomorrow at 2:20 p.m. He's a real AI expert, and he's developed, together with the team, a new photonic quantum machine learning framework, Merlin, and he will certainly tell you more about it tomorrow. Okay, now we have use cases. I said we are here in the quantum AI space, very roughly speaking. The next phase is really about increasing qubit count, and we know that from 40 photonic qubits on, our machine will provide an advantage. So we're looking into other applications in quantum chemistry or energy, and then of course, ultimately, we're of course interested in the fault-tolerant era and solving the big problems. So this is really the application roadmap, and of course, we do have a technical roadmap where at the moment we're here with 12 qubits. We want to roughly double in the coming years, each year. And in parallel, we're going to develop logical photonic qubits. And that's what I'm going, or logical qubits, I should be careful. Logical qubits, I'm going to tell you more about that from now on. So that's the rest of my talk. I'm going to tell you how we're going to reach the fault-tolerant regime with Quandela. Okay, and if you're interested, we've got a roadmap brochure where this is laid out in more detail. Okay, so typically one way to reach a fault-tolerant regime for photonic computers is to use measurement-based quantum computation and to generate these type of logical qubits, photonic qubits, via what we call fusion, okay? So what you do is you have a single photon source and you stitch together the individual photons in a more and more complex degree, such that you build up these very complex entangled states. So each link here corresponds to entanglement between photons, and you end up, it was shown that this 24 photon state is a very useful state for implementing a fault-tolerant architecture. And this is exactly PsiQuantum's approach. So they use parametric down-conversion sources to generate that single photons. They use optical chips to provide the entanglement and fuse the different photon states to stitch together this 24 photon state. However, in order to get one logical qubit like that, if you do it all photonic, you need 1.6 million of these sources. You need more than 1.6 million detectors, and you need corresponding phase shifters to just produce one logical qubit. Okay, I'll let it sit like that. Now there is a smarter way. You can harness the single photon sources that we have, and we have these quantum dots sitting there. These quantum dots, they not just serve as a single photon source. They also can carry spin. If you inject an electron or a hole in there, they can carry spin, and you can use that spin degree of freedom. And you can use it, you can control this spin very nicely with lasers, and you can generate entanglement that way. And this was done in Pascal Senelar's group, already published in 2023, where they showed high rates of entanglement generation. And very lately, they have been able to generate these cluster states here, these caterpillar states, as a base for fusion. So you could now go use this and stitch together these states to build again a logical qubit. Turns out you can even do better. And here comes Quandela's approach, right? So the idea to do it is to use the photons to implement entanglement between different single photon sources. So assume you've got a single photon source, but not just one, but 12, okay? So you use 12 single photon sources, and now you do what we call a repeat until success gate to entangle these different quantum dot sources with each other. So essentially what you do is you emit photons from each of the quantum dots involved, you let them overlap on a beam splitter, and that generates entanglement, essentially. And you just build up your entangled state at the level of the quantum dot. And you end up here, and actually, in fact, you could stop here, and that's where I'm going to come back in a moment. But in principle, you can show that if you do 2 emission events, then you end up generating that 24 photon entangled state, which corresponds to a logical qubit. And that way, you only have used 12 sources, 24 detectors, 24 phase shifters. And if you're very conservative and assume very positive numbers for parametric down conversion and so, you end up, you can show that you end up being at least 100,000 times more efficient than a pure photonic approach. Okay? Now, as I said, we don't even want to generate photonic logical qubits. We actually will stop here, and we just do the measurement-based modality at the level of the spins, okay? So this is the spin optical quantum computing approach that Quandela, the SPOC architecture that we propagate. So in the boson sampling mode, just to switch back to the beginning of the talk, if your chip gets too large, the problem is that you at some point you just cannot overcome the losses. So to realize more than 100 qubits in boson sampling, it's very, very, very hard. In this case, in the RAS architecture, or the SPOC architecture, so to speak, RAS is repeat until success gate, the photonic chips which entangle the spins through the photons, they're very simple photonic chips. So they're small, they can be fabricated with low loss, it's not a problem. So you've shifted away from the problem of making larger and larger photonic chips. The price you pay, there's nothing like a free lunch, of course. The price you pay is that your sources must be very good, and you need many, many of these single photon sources. I'll come back to that. You also need some photonic routers with electro-optics, but the community is developing that, and there's no big blocker there. So in the end, what you need to do is, you have these modules, and you stitch them together. The nice thing is, it's modular, it's interconnected, because in principle, these single photon sources are fiber coupled, and you stitch everything together with fibers or optical interconnects. The whole thing is totally modular. You can immediately think about distributed quantum computing and so forth. The whole thing has a very low error threshold. I'll come back to that in a moment. And the whole thing is also very efficient, as you've seen, resource efficient and also energy efficient ultimately. So that's a really big advantage. And just have a short video just highlighting that again. So you've got your spins, you've got the photonic routers, you've got your photonic chips which entangle the spins with each other. You detect, and you know that you've got entanglement once you see the green light. Okay, and in principle, you can just concatenate these modules and connect them up and scale them up. Okay, and the nice thing is you need to optimize one of these modules, learn how to get into the good regime, and then you copy those, and you're done. And just for the geeks, I'm not a quantum error correction person myself, but I thought it would be interesting for the experts in the audience to just see what the different loss budgets are. So this was in the very first architecture paper that the group published. There was a surface code implemented. This is a Floquet code, and at the moment the team is calculating LDPC codes. And just for you to have an idea, so the typical photon loss you can allow yourself in this architecture is around 6.4%. The spin coherence time, which you need to now worry about with the quantum dots, is, so this T-Rus gate is the typical gate time for your entangling gate. That is also within the typical numbers that you can achieve with quantum dots. And then also photon distinguishability is actually not so stringent, and it turns out that in terms of distinguishability, the LDPC codes look very good. You can allow yourself a 10% error there, something like that. Anyway, so as you would have seen, the key to success is to scale up everything and industrialize the whole production of the machine, but in particular also the production of the quantum dot single photon sources. This is a fiber pigtail one, so the photons, the quantum dot sits down here somewhere, and the whole source is directly connected to a fiber. And we have got all of this part of the value chain, we've got already in France, at the IPVF in Palaiseau, but we don't have access to our own MBE machine, molecular beam epitaxy machine, for growing the initial material, the initial gallium arsenide wafers, out of which we make the single photon sources, and that's going to happen in Munich. We're going to build such an MBE machine, actually in fact two, and we're going to produce our own wafers for Quandela. And we're also going to build, this might be interesting for some people in the audience, a quantum algorithms team and also a theory team here, and we're building a business team, of course, as well. And with that, I'd like to thank you for your attention.